بسم الله الرحمن الرحیم. لا حول ولا قوة الا بالله العلی العظیم. حسبنا الله و نعم الوکیل. نعم المولى و نعم النصير. Today we will continue the the interesting topic we started last time regarding the screw method or successive screw method for forward kinematic analysis. As I mentioned, this is somehow magical, and how it works is very perfect that we can work with that. The issue is going with definition of the screw as a mapping rather than just an orientation, since the screw representation can provide us with both rotation and translation in terms of motion transformation. As we mentioned, we can, if we could possibly represent the motion with the screw vectors, not vector with the screw tuple or representation. And then from the screw, which has a physical meaning, we find the transformation, the homogeneous transformation. So basically, and this could be found for any kind of coordinate system that we have. This is not restricted to just the base coordinate frame, but we just need a coordinate frame to represent the screws and find the transformation. And furthermore, we need the end effector, position and orientation as a frame. So we need another frame, which is usually on the end effector, or if we would like to solve for the wrist position, we can put a frame on the wrist. So we need only two frame assignment. One is the base, and the other one is the point that we are finding the kinematic analysis for that. And then after doing that, by simply the definition of the homogeneous transformation we gave in the last chapter, we find the homogeneous transformation and then use the mapping. This is the final version I have put here. We know that the orientation of the end effector can be successively found by the orientation of successive screws, in which, as we mentioned here, the theta parameter or the d parameter, depending on having a prismatic or rotary joint, or some joint variables. By this means, then we can use this loop closure representation, not in a term of a matrix form, but a bit more than that. We call it, as we see here, that if we have a reference vector of the end effector, if we could represent the end effector vector in a reference frame in some particular very simple orientation of the joint, then by doing a consecutive mapping by the screws, this could be represented in the most general form of the moving platform or the end effector, and that this can be basically defined as the forward kinematic. It is very, very different from Denavit-Hartenberg, and very, I guess, more physically intuitive and useful in terms of representation. Now, if you look at here, we give it 2 or 3 examples. As you see, the examples are much simpler. Suppose that we have 3 arm manipulators here. We have 3-4 manipulators here for the representation, as you see. The first one is a 3-arm manipulator. The 3-arm manipulator is quite simple. We have solved the kinematic relation by means of 2 or to other methods, direct geometrical approach, or having the Navitt-Hartenberg problem. Here we use the screw representation. Look at the steps that we are doing it one by one. First of all, we say that consider a configuration that all the joint parameters, all the joint variables, the theta i's and d i's are equal to 0. As you see, this is a fully extended arm, as you see in here, where the theta 1, 2, 3, which are the joint variables, are equal to 0. If this is the case, this could be for 5, 6, or more variables as we wish, but all the joint variables we consider to be 0. By this, we call it a reference frame or a reference position, or we in robotic also we call it a home position. It is a position that we consider starting the motion from this point. And as you see in here, by this means the screws could be very simply determined. We have a motion from here, so we have a screw 1, motion about this joint, screw 2, and the motion about here, screw 3. And we have one point as well, which is the point of kinematic analysis that we want to know. This could be a wrist, P point, or Q. Here we do it for the most general one. Consider the Q one. I have written both of them, and you can do for both of them. Q at this reference coordinate or this reference position is very simple. As you see, we have one reference frame X, Y, and Z. So Q is with a length of A1 plus A2 plus A3 in X direction. And you see that this is in X direction. Furthermore, if you would like to find the orientation here, you could give any orientation coordinate at that point. So if you use here a UV, which are very similar to XY, the UV, the rotation matrix would be I. So we consider the vectors of the rotation matrix as U0, V0, and W0. As I mentioned here, usually we have the target position and the reference orientation and position with some UVW coordinates. This is just to represent the rotation matrix by their vector components. By this means, as we see, we have the reference coordinate quite easily. Now we find the screws. The screws should be determined by 4 parameters. The direction of motion, which we call it the Z or the S, and the translation or the difference from the arm or the length that we have the screw coordinate with respect to the base frame. So here, as you see, there was some problem in the previous version. Here, everything is corrected. We have the screw coordinate. All the screw coordinates are in Z direction, as you see. So they are 0, 0, 1. And we need also the X1, X2, the S01, S02, S03. S01 is completely 0, but S02 has a length A1, and S03 has a length A1 plus A2. And what is the joint variables here? What is the variable that are changing? Of course, we have theta 1, theta 2, and theta 3. By this means, as you see, we have a number of parameters being set. Let me just make the student all as presenters that they could contribute in the class, please, anytime you have any question, just open your microphone and ask your question, or just raise your hand that we can continue. By having this S0 and SI as 0 and determining the joint parameters, the joint variables. The joint variables are either θ1 or D1, depending on the revolute or prismatic joint that we have. And as this goes by this means, the only final point that we need is the target position and orientation. The target position, we call it with the Q parameter, QX, QY, QZ, the most general point. This could be anything in the space. Like consider you have something like here, QX, QY, and QZ, and we know that the QZ is equal to 0 since it is a planar case, and also the target pose that it would have, it has a orientation here. The orientation here could have any variable phi as we see in here, and this could be represented by UVW, and then we can represent these two together. Now, since this step is done, the reference frame, the screw coordinate, and then the final frame is basically done. Now we can continue working on that. Just give me, I'm really sorry for that. It's a small interruption here. I try to make it less interrupted. Now, since we have this table in here, then we can very simply find the transformation. And this transformation is totally different from the Denavit-Hartenberg transformation in terms of the structure that we designed it. This comes from this formulation. We gave it in the last chapter, but as you see, there are so many parameters here. We have v theta and so forth and so on, but the end result is quite simple. We have this, we can multiply these three together to find this representation, and this is the golden rule, or the magical rule, that when we have a position being considered here as Q0, the position that we have, the end effector as reference frame, this can be moved to a general coordinate Q by just mapping by the consecutive or successive screw mapping, A1 times A2 times A3 multiplied by Q0 gives you Q. And then you find the solution rather magical. The magical coordinate is like that. As you see, Q0 times this 3 gives you Q, and it is very simple to multiply this by Q0 that we have found here, a simple A1 plus A2 plus A3, and that goes through the Q1 as we see in here. And by multiplying this to the Q0 vector, we have three equation here. The three equation is as we had before, QX, QY, and QZ. And the orientation, as you see, the orientation part gives you that we have a simple addition of the joint angles as the final orientation. And just the shorthand kinematic relation is as we had before, A theta 1 plus A2 theta 2 plus A3 theta 1 to 3 gives us QX and QY with the same similar manner. This is somehow fascinating and very, very strange in terms of how this is working, but as you see here, we have a golden rule here the successive screw coordinate. And consider that the main difference is that the screw has the mapping that we represent with the screw has a physical interpretation, that we have a motion about this plus, as the Schall theorem says, translation along it. So let's see, maybe it is only true when we are in a planar case. If we are in the most difficult or most general form, does it work the same way? Yes, it works very, very effective. Here, I put a very general manipulator here, 6 degrees of freedom. I didn't go through the 2, 3, 4, 5. I just go to the end one, and you should practice this. This is the 6 degree elbow manipulator. We have 3 degrees of freedom for the reach, as you see, and 3 degrees of freedom as the wrist. We have this in many manipulator. We don't consider an offset here in this manipulator, but we have all R manipulator, 6R manipulator. What we do, again, we consider that all the theta i's are equal to 0, and we make the robot fully extended with 0 orientation at the angles. So if we just make an extension like this, then we can find the screw axis. As you see, the first one, we have a out of plane orientation or rotation here. So the screw 1 is this way. The other screws are all out of the plane. S2 is here, S3 is here, and S4 is here. And then we have this wrist position. And the wrist position, as I mentioned, is usually the ZV, or ZUZ. Here we see, as we have this orientation, S4, then at this point position, the U position, and then at the V position, or V orientation. So we have a 3 perpendicular screw axis here, and then the final point, we could consider the Q point or the P point or the wrist point. If we consider the wrist point here, which we call it P, it is much easier. The transformation is much easier. But if we consider the Q1, the very last ending point of the end effector, which we call it Q, then it is very easy to write the target position. As we see, we have the Z. We need also the orientation of the end effector. We consider it as we like. Consider that we are using U0, V0 here. Of course, it could be any direction here. Just keep it in mind. And U0, V0, U, VZ is inward, and XYZ, as you see, XYZ is also the Y goes to inward. And the screw axes, as we see here, are out of the plane, outward of the plane. So the UV orientation vector that we see in here can be represented with respect to a fixed frame. Again, here consider that the fixed frame could be considered at the bottom point of the base. Then we have this length, the D1, always coming through the picture, but it is much easier to consider. You can consider the reference frame anywhere you want. I consider it on this point, just to make it much more simpler, to don't bring the D parameter, the fixed parameter, into the picture, into the equation. So we have XYZ, the fixed frame here, and the moving frame here. Then we have the orientation and position. The position of this point is fully extended along X. So we have A2 plus A3 plus A4 plus D6. This D is a fixed wrist to end effector point. As you see, A2, A3, A4 plus D6 along X coordinate. The other angles are not important. The orientation that we have U, V, U is along Z, as you see. So it is 0, 0, 1. V is along X. W is along X, and if you have UV, W, V is outward the plane, so it is along minus Y, when Y inside that. Of course, if you use P, this D, this offset D value is not apparently here, and we can work with both of them. We can use the golden successive screw mapping for both P and the Qs. And you can see here, by this means, when we have this parameter, now we should write the table of the screws. The screws can be seen quite easily, as you see here. The first screw is along Z. All the other screws are along minus Y. We call it with this one. And then we have, again, S5 along Z and S6 along X. As simple as that. In 2 minutes, you can find the screws. What is the position or the difference of the screw with respect to your reference frame? This means this is related where you have considered the reference plane, where we have the reference frame on here. So we have A2 for the S3. So S1 and S2 have 0 positioning or S0, but Z3 has A2, then we have A2 plus A3, again in X3, and then we have A2 plus A3 plus A4 for the S5, and the S0, as you see, S0 is intersecting with our frame, so we have 0 here again. We have SI and S and S01. We know that we have θ1 to θ6 as the joint variables. We can very simply, the target point is generally written as we use here. Again, we have a general Px, Py, Z and general rotation matrix, and then we refine this. You can write a symbolic MATLAB manipulator function that you can just give the parameters here and find the transformation. These homogeneous transformations, especially these two, are totally different from the Dinavitt-Hartenberg. You find in Dinavitt-Hartenberg it is much more difficult to find that. Of course, you should learn that too, but here it is much more easier to find the screws and find A1 to A6, and then you use the loop closure method. As we consider here, the loop closure method is that you should multiply all of these and then put it on here and find the final position. This gives you a very long version of the kinematic relation. It gives you 3 relation for position and 3 relation for the orientation. I haven't go through this, but you can simply use this as the final kinematic relation. For a 6 degree of freedom, the kinematic relations are very extensive, as you can see. We can do the same thing with the arm. Yes?
Did we use UVW in our analysis?
Which UVW? This one?
Yes.
Yes, we have used that since we are using this 3 coordinate in the reference frame. In the reference frame, it gives you the orientation when you are in the home frame. So we have an orientation here. This basically, when we are using this, okay, you mean that in our analysis. Very good question. Like always, Zahra, you are taking me thinking. When you are using these parameters, the positions are more important than the orientation. Why this is useful? This is useful only when we are using this UVW in the target position. Depending on the orientation we get here, the target orientation will be different. And this is a reference orientation vector that we get in the kinematic formulation that we have. This has not been directly used in this equation. As you see, in this type of equation, only the positions are being considered, but it will be somehow indirectly comes into the orientation formulation that we have. Very good question. Thank you. And this is my final, here we will see, let me see, this example you can find the result when it is going on. In the final example that we have in here, we consider also a manipulator with a prismatic joint. Now when we have a prismatic joint, then this is not just the theta i's as the variable. Again, we do the same old thing. So we put it into a very simple, fully extended arm with all theta i's and d i's equal to 0. If we use this, you should have a physical understanding or shape of the robot. The robot has an offset here. As you see, the base and the arm are not along each other to have a full orientation of the second arm. So we have a G, we call it a G offset here, a term that, a completely constant term that shows you the offset, but then we can have the screw coordinate. If we go through the screws, we can find the motion of this manipulator. We have done this before in the Navier-Hartenberg representation, but in here it is much easier. Here we have the first orientation or rotation, we have screw 1. The second one is this arm coming up, so S2 is equal to here. And then S3, as you see, S3 is along the position that we have. And when we are considering that, for the reference point, we consider the position of this equal to 0. No, the D3 to be equal to 0, like the theta, which is equal to 0. So it is fully folded arm, of course, in here. And then we go ahead here, we have orientation along this arm, so S4 is in this direction, and then again, like usual, we have a wrist, a 3 intersecting coordinate. In here, it is like a Z, Y, and again Z. For this manipulator, the direction can be found by this 3 orientation very simply. Again, we have 2 point, 1 point P is for the wrist, which makes the formulation much easier if we just want to find the wrist. And if we would like to find the edge position, the end effector position, we have again an offset edge parameter, a distance, a fixed distance edge also in our orientation formulation. Now, if we consider that for in general, now we can go forward and find this position and orientation being written. Again, we have the frame, the fixed frame, we put it here on this point A. It is, we could put it on point B as well, but usually we consider it on a frame, fixed frame on the base that can be rather measured. If we put this one in on here, then we had different variable for the S0s, but here it is quite simple. Here is the fixed frame X, Y, Z, and we have U, V, W at the end effector. It is the point at the end effector. Now, the end effector position, X0, if you see, it is very simple. If the D3 is equal to 0, it is completely folded. Then we have only an H and a G. So we have a G and H, G in terms of X and H in terms of Y. So we have G and H for Q0, very simple. And this is very, very important. And if we consider the wrist position, then the edge is also not coming into the picture. We have G00. And then it is important to find the screw coordinates. The screw coordinates are given here. Unfortunately, I guess. No. Yeah, here. I'm sorry. The screws are the next page, as you see. I go through just a few of them, and then you can continue. We should have this figure here to see here. For example, S1 or screw 1. So it is along Z direction, and there is no S0. So you see that this is along Z direction, there is no S0. What about S2? S2 is along X direction, and again there is no S0, no offset. You see here, it is along X direction, there is no offset. But for example, S3 has an offset of G. The offset G is in X direction, and S3 is along Y direction. So you can go through the Y direction. As you see, this is along Y direction with the offset G along X direction. With the same case, you can go further and find S4, S3, 4, 5, 6. When you have this, you put it into the target position. Basically, you find the A1 to A6, and usually since we have an arm and a wrist, we can have two kind of position. We can have a simpler where just don't consider the wrist. If we consider the P position, then it is much easier to find the position of the outreach of the robot at the forward kinematic, which is Px, Py, and Pz. I didn't recall that. Again, Px, Py, Pz is very, very simple, very general. We can consider it as general point P, X, Y, Z in the space, and general rotation that we have Ux, Uy, and Uz. And if you consider the position P here, and if you consider Q, then Q can be found if you give the full position for the Q. P and Q has related like this, two together. Again, if we go with the P position, we need only the first three consecutive points. As you see, the P has been targeted or has been motion mapped along S3, S2, and S1. By these three consecutive screws, we reach to the point P, and from point P to point Q, we have three orientation or the wrist manipulator here. Of course, in forward kinematic, it is not important, but as we see in this chapter, in the next part of the chapter, in inverse kinematic, we usually divide the wrist from the arm to make the inverse map quite easier. We'll go talk about that. Again, here we have three positions for the wrist, and then we can go for the orientation. As you see, we have an orientation with R5 or A4, A5, A6, which are R4, R5, and R6. This gives the orientation of the end effector. This could be quite similar to what we see in for the orientation part. So by this means, we have find some nonlinear equations for relating the position here from end effector to the joints. Let me just conclude this part with some notation that we use, very simple notation, and then I give you some time for questions and answers, and just stopping me here. Usually we rename some base frame, for example, with some notations. For example, base frame the base frame is considered with the B frame We have also station frame. Usually the robot is put somewhere, but the workspace is on a station or on a conveyor or on some place that can be should be picked up or should be manipulated. So if we have a S frame, this S usually is considered as the station frame. The wrist is very, very important, as I mentioned. It's one intermediate point that we can use it for many inverse kinematic problems. So W, whenever we use W, it is for the wrist. And we have tool frame. Usually the end effector is called with E or Q in the Tesai book is Q, but usually we use E for the end effector. And if we use T, this is the tool, not the end effector. Maybe the tool has some elongation and this tool can be changed. We have different tool to be put on the robot. So the end point of the tool, the point that you are really manipulating the targets are usually the T. And we have also a goal frame. The goal frame is on the subject that we have in our workspace or in our station that we would like to manipulate. For example, we would like to do welding or cutting or painting or whatever we would like to do. And we have this similarity transformation as we see as a map. We can use, if you would like to, the robot to go to this goal position, we need to have the transformation, the theta, such that, for example here, that the T with respect to this S frame, if we could make the T with respect to S frame equal, which is T to the S is an external point, but as you see, we can go from S, from T to W, we can from here go to the wrist, and from wrist with some manipulation go to base, and the base we can go for to the station. And this should be calibrated quite accurately. Where is the base with respect to the with respect to the station? And by this loop closure, the global loop closure from here to here, if we have this point with respect to this, usually we would like to go, this point should be at this goal position with some angle or with some orientation. So how we do that? We just make it kinematic relation, kinematic equation that the T G with respect to S should be equal to T with respect to S. And by this means, we can usually manipulate the robot to the end effector. And practically speaking, up to now, we talked about the mathematical representation. And I prefer to use the screws because it is much more intuitive in terms of mathematical representation. But physical representation, if you would like to have some physical representation, how we use this, there is usually a teaching pending. We just move the robot by moving the joints, and we can make that end effector point to directly go to the position that we would like to have the robot at that position. And usually we move the robot manually to this point, we save this target position, and then we can give a control algorithm that we can go to this point several times in space. So by this means, the first part of our chapter, which was forward kinematic, is concluded. And now I'm ready to go to the more challenging part of inverse kinematic. If there is any question, please stop me here and ask your questions.
May I ask one question?
Sure.
I had an interpretation from the preceding example. Aren't the physical constraints important for preparing the robot to write the equations? I mean, for example, if D cannot be zero by physical constraint, we don't mention it at all. we just set it zero to write the equation.
I will go through that in a few more next slide. We put the constraint for workspace determination. You know, right now, for mathematical representation, we just want to know how Q is affecting, you know, for example, X, Y, or Z. But of course, Q could not be equal to infinity. It's always bounded. Our theta angles are bounded. Our extension of the prismatic joint are all bounded. When we bring this into the picture, just bear with me a few more slides. We talk about some more important issues here. We should write the equation first, and we should make sure that these equations are correctly written, and then we should analyze it. In the analysis, we have this all. We should consider all of this constraint. Not only the constraint, there are some much more detail that I will talk about it in the next slides.
Thank you.
Thank you for the very good question.
Excuse me, Doctor.
Yes?
Good morning.
Good
I have two questions.
First, ask your second question, please. Okay, go ahead.
Page 39 in the slides.
I am very happy that Hussein last time considered there was a problem with my. Let me also, before going through that, Hussein, there were a problem. Where was the problem? I don't remember. I guess we had a
25, I think. 25, I think.
25. Yeah, just to make sure that. Yes, and
24
maybe. Yes. Yes, just there were some problems in my notes that Hussein mentioned last time, but I didn't realize at that time. After the class, he mentioned that there is a mistyping in here. There is no, these two should be interconnecting. Therefore, there is no A0 here. We put something wrong. But anyways, you told me about 35, yes?
39, please.
39?
Yes.
Yeah.
Here in 39, you mean that when multiplying the successive, yes, A1, A2, A3 by Q0, we will get Qx, Qy, and Qz? Yes. But multiplying this matrix by Q0 by A1 plus A2 plus A3 0 0 transpose. We didn't get this matrix.
I didn't say that this is true. I said that Q0. I didn't get your question. Your question is if you considering the inverse of this equation.
No. This Qx, Qy, Qz can be computed by multiplying A1, A2, A3
times
into Q0.
Yes,
times the Q0.
Yeah, that's it.
If we replace here Q0, we can't get Qx, Qy, Qz like this.
Why? Why we can't get
If we place here A1 plus A2 plus A3 0 0, multiply this matrix by this matrix, we can't get A1 cosine theta 1 plus A2 cosine theta 1 2 plus A3 cosine 1 2 3.
I still don't get your point of question. Are you arguing that this equation, is it right or not, or this is not your question?
No, this is okay. Not my question.
Yeah, what is your question again? Make it clear. I am not sure. A plus.
No. If I put here, if I multiply A1, A2, A3
here
by Q0.
Yes, by Q0.
Can we can't get this solution.
Sure. Why we can't get the solution? What is the problem with that? We have a vector here. We have
Yes, yeah, no. Sorry. Put here A1 plus A2 plus A3 0, 0, 1.
0, 0, 1. Q0 is 0, 0, 1.
No, Q0 is A1 plus A2 plus A3. Sorry, A2 plus A3 plus A4.
Plus
before.
0, 0.
No, you must go before, please.
Yes, here, Q, here, exactly.
Yes. Yeah.
Okay.
If we put it downward.
If we put it here.
Yes. Can we get this solution?
Okay, you mean that this is not right? Now I got what it is.
No, my question. No, it's a question, not. I'm asking, only asking.
Yeah, no problem. But I don't know what you are asking the problem. I mean that, very simple. Okay, I will explain. Maybe something will be clear. We have A1. Do you accept that the multiplication of these three matrices, which are 4 by 4 matrices, is something like this?
Yes.
All right. So we have a Q0 here. Do you remember? Do you accept that Q0 is this? This is no problem.
No, before.
Yeah. This is 3 by 1, but this matrix is 4 by 4. So we put a 3 by 1. We add 1 here. Yes, we know that. So we have a 4 by 4. Now we multiply this by Q0. Now, if you consider that Q0, if we consider that the Q0 has only the X component, we have only QX, and we have no QY, no QZ. If we put it here, we have C theta 1, 2, this part multiplied by QX, which has a non-component. So this part, C theta 1, 3, 2, multiplied by this equation, okay, by this, gives you the QX version. The QX is this one. Okay, now you mentioned that this is not right. Okay.
Because we have A1 plus A2 plus A3. It must all be multiplied by cosine theta 1, theta 2, theta 3. Not A1 cosine theta 1 plus A2 cosine theta 1, 2. Sorry.
No, very good. Let me just think about it. It is very good to make me thinking. So you're arguing that this we are making a this is the one. Yeah. Okay, I understand now. What would be the problem? You see, we have a 1 here. We have. And consider now I understood. We have A1, we have QX here, something, A1 plus A2 plus A3, 0, 0, 1. Yes, you accept me?
Yes.
So when we have the 1 here, this A1 plus A2 plus A3 will be multiplied by this.
Yeah.
And then we have 1 multiplied by this.
Yes.
Okay, what will be remaining? We have A1 here, A2 C theta 1, theta 2, like this, and then we have A2 plus A3 with minus sign, and A1 plus A2 plus A3 with a plus sign.
Yes.
So what will be remaining? This part.
Yes. They will cancel each other. They will cancel each other.
They will magically go to the point that you require.
Yes.
It's
magical.
It is magical.
I asked this question, and my mind is for the H parameters. It's like magic.
No, just forget about the H parameters.
Yes.
This is the true magic. No, it is not magic. It is a physical concept. It is totally different from the Navier-Hardenberg problem.
Very simplified. Sorry, and 41, slide 41.
I'm sorry not to understand your question. That's the...
sorry.
It takes a while that we can get more communication. Now going to 41.
40. Why did we put SO6000?
This one?
Yes.
Because this S6 is just intersecting the reference frame.
But we have distance. We don't have distance.
No, it is.
Oh, yes. They are aligned. Okay.
This is good, Hussein and other people. This slide seems simple, but when I wrote them, even when I write them for the class, it seems to me very simple. When you look at the book, it seems to be very simple. But I encourage you to do it yourself once. Try to repaint this painting again. Draw this painting by yourself. And I think it is very good that you write a program to do that. Because this is, as you see, this manipulation, when you write a program, you get this equation quite easily. Maybe by hand you made some mistake, but write that. Try to put your picture into the story, and this will change the understanding that you have about the concept, especially for the screw. And I mentioned, we are not with the screw. We are not done with the screw yet. We have opened a new story for you, and we will talk about screw several more times. And this is not given in usual books. This is not very, very intuitively known by all the people. But the student of my class, I make sure that they could understand the concept and then use them. And if you can, it is a bit hard to get into this point that you feel comfortable with the screw. But when you get comfortable with the screw, then you considering why doing such a hassle of dinner with Hartenberg. It is a hassle. But anyways, it is.
Thank you.
It is really magical. And try. I give you 3 examples here, and in the assignment, I will give some other example too. But before going to, is there any other question? Hopefully not, because I want to do some topics here. But let me just show you about what I require from you. I gave you a research. As you see here, of course, it is in Farsi here, that the number of people in my class who have registered into this class, of course, in the LMS system, not in the Gulistan. In Gulistan, we have 15. And we have some more students, adding as a guest. There are 21 students here. And our research, the first research, which is very simple, only 10 of them have given that. And this is too bad. You see that Muhammad Ali has not given that. Some people have done. Pariya, Mehran, not given that. Erdogan John, Muhammad. But for me it is very important that you come with me. We have started a journey together. I don't want to be alone in this journey. You see that some people have not given that. You see these are being read. Alireza John, Alireza Azizam, and some other. I don't want to rename کارشناس آموزش دانشکده برق هم didn't give that. But you see, for me is what Hussein has given that. That's good. Maybe I don't go through all your solutions and assignment, but it is. We have started a journey. Again, I don't want to enforce you, But if you don't come with me, if you don't follow me, then I don't have energy to continue this journey in myself alone. And I request all of you, when I give a research, of course the research is optional, but I think it is very enthusiastic to get at least a few simple words that I have worked on that I still have not find what shall I do here. And I don't like a classroom which I'm just talking and everybody is just listening. And I do need a classroom. I do prefer a classroom that the people don't let me talk. They just contribute and work further than me. And then I will be I have so more power and energy. And believe me, I will give so many energy to you. I put so many energy to this class that you have never seen it before. But this is a two-side relation that we have. That is my request, my خواهش، my تمنا، whatever you say. استدعا میکنم همراه باشید. اگر همراه نباشید منم خسته میشم و همه آدما خسته میشن. Anyways, I just forget this part, but from now on, please continue working on that. Some of people said that the deadline for the first example was too tight. It was our problem. Yes, I extended to this Friday night that you have at least enough time to work with that. Perfect. Now let's go to the second part of the class, which is inverse kinematic for robotic manipulators. We have about 15 minutes time, and that's enough to give you in this part, I will give you some hints, some very important hints and some clues that has been taken from the mind of many scientists in this field. Inverse kinematic, there are so many books written on just inverse kinematic. There are so many papers that are written on just inverse kinematic. There are so many researchers in the world that have put all their life just on inverse kinematic. They call robotic, they see robotic as just inverse kinematic. So it is really influential. And for me, of course, I don't want to put that much emphasis on it because I'm a control man, not an inverse kinematic man, and I'd like you to, learn more control. But without kinematic, it is impossible. But there are some the most interesting issues between the physical concept that you can see in a robotic with some mathematical background comes in the inverse kinematic. And of course, it is a very challenging problem. When I say so many people have worked on it, means that there is so many problems, so many open problems, still so many open problems. When I was taking this course, some of this problem has not been solved, and we were talking about, getting to that point. Up to now, there are many of them are solved, and there are so many interesting approach here. Unfortunately, we don't have time to just spend on the inverse kinematic the whole semester, but it could be possible to do that. What is inverse kinematics? Inverse kinematics is very simple in terms of the concept. So that if the joint space variable are given to you and you want to find the task space, either by Denavit-Hartenberg or Screw, you write the equation that if this is given, you can find the task variable. The task variable are usually, if you have a fully actuated manipulator, 6 degree of freedom manipulated, tuple of 6 coordinate, 3 for position and 3 for orientation. Now, Inverse kinematic is the inverse problem. Consider that x, y, z is given to you and you want to find q. Why it is important? Let's first think about when we use it, where we use it. Suppose that this cup, of course you cannot see, this cup is here. I should put it here, unfortunately, to have it in the picture somehow here. Also, this is the Case Western cup. One of my former students who have been graduated here has given this cup to me. And this is my manipulator. And I want to drink this water. So I should go and take this cup handle in a direction that I can drink it. Yes? So I have a motion to go to there. What will happen in my mind? How my control system will control my manipulator to do that? There is a position and orientation here, which is x, and I want to reach to that point. So I should give motion. If I go this way, I increase my theta, it is not good. It should be closing my arm and going to this direction, and look at my wrist and my fingers. It should go here and touch that so that I could keep this and drink it. So this means that there is a given position orientation, and we want to reach to this position and orientation. And what we should do, we have the theta angles of our arm. How we can go to this point is this way. So we have a desired position and orientation, and we need the desired joint space variables to reach to that point. And we do it so easily. Even if I take my eyes closed, I can do that. Maybe a bit with some problems, but I can do that. And again, I can drink it. And then I can very simply leave it on my desk. There is another position and orientation. And it shouldn't be that way. If I put it that way, everything will be full of water. So it should be vertical. And again, position and orientation of the task space where we are working. Now look at the painting. What our fingers is doing. Look at the writing. You want to paint. You want to write. You want to have so many works done with your hands. And this is only done. You know, or you see that this is a visual feedback we have also there. We would like to go there, and then we can do that. Given task space variable x, find q. For now, let's say that x desired and q desired. And in the final part of our control system, we say that to do that, we need a control action. We need to have some muscles working, giving some torques or forces to our hand to work that. But for now, for the kinematic part of the motion, we need to know the task space, and we would like to go to this space. Now, this could be considered just a simple mathematical arithmetic. If forward kinematics is some nonlinear problem are given from here to here, which we find it at least for 10 manipulators now in the class, seems to be very simple. Now we just inverse this problem. But usually inverse problems are not so easy. First, by basic concept, we solve the loop closure equation by considering that x is given and q is fine. When we say x is given, it means that te with respect to 0, this is given. Te with respect to 0 is given. Or Tn with respect to 0 is given. Since we have X, the orientation and position, and we would like to have all the detail Q1, Q2, Q3 that are generating this motion. So if we would like to do that, usually we need some direct inversion, but it is usually impossible to do that in direct inversion, because the direct inversion, you have a fully embedded nonlinear equation. You cannot simply inverse them. So there are so many works to do that. The main important way is to separate the orientation from the position. And we do that with putting wrist into the picture. We have usually our orientation with the wrist and the position with before we have an arm and a wrist, usually 3 degrees of freedom arm and usually 3 degrees of freedom wrist in Manipulator. So we usually try to separate this problem into 2 problems. If we can do it, if we can separate it in 2 problems, the problem is solved. A very difficult problem is solved. Two difficult problem, but less difficult problem in terms of Qs, and then we can solve for that. So we come to many important issues. And these issues in robotic has physical meanings. And this is amazing. This is really amazing. First, solvability. Is it possible to solve? This is a mathematical question. Existence and uniqueness. Usually in mathematics we have a theorem of existence and uniqueness. But here we don't talk only mathematically. We would like to talk physically. We would like to interpret that. First of all, the vector loop closure equations are nonlinear, and I call it trigonometric. We have sine and cosine, so many sine and cosine, and the addition, multiplication, and they are nonlinear. And is there nonlinear? We have 6 equations. For example, if we go back to here, you have just to look at this problem. Just look at here, just this 3 problem. Qx, Qy, and theta e. The simplest possible forward kinematic that we have. Now, if Qx is given and we would like to find theta 1, theta 2, theta 3, this is a nonlinear equation. The inverse problem is nonlinear since we have cosine, and it is trigonometric. So it is not very simple. It might have a solution, it might not have solution. You know that in a... But what does it mean it does not have a solution? This has a very important meaning to us. First of all, for a 6 degree of freedom manipulator, the number of variables are 6. The number of equations, how many equations we have in a kinematic loop closure. If we write it in a geometric form, we have the same number equation as the number. But if we write it in a matrix form, as we did in Denavit-Hartenberg, or even in screw coordinate, we have 12 we have 12 equations, 9 for orientation and 3 for position. We have usually 12 equations with 6 unknowns, but we know that these 12 equations are not independent. They are related to each other. So maybe we can use only 3 of these 9 equations. This is a choice, an engineering choice, which makes us very simple, but it is somehow dangerous because these 3 equations might not work everywhere. It is very good if we could use all 12 equations to find this 6 parameters or 6 unknown. And this caused the problem more difficult. You have seen the inverse problem in Euler angles, relations, and the degeneracy that we call, and the research I told you, and I kindly asked you to work on it, and only 10 people have worked on that. Not all of the students. We need that. If it was not important, I didn't tell you to do that. Here you see that usually student-wise talking, we find the simplest equation that we can find the inverse and get that. This is a way to do that, but this is not professional. Usually it is important to use all the equation, and somehow it is a hassle to do that. Finding the solution is difficult, no matter what, no matter how simple the equation is. But if you have some physical understanding, if you have some physical insight, then the mathematical representation would be, again, simple. I will just continue this part. I don't go further, because I request you to think about it. When there is a solution or when there is not a solution, the existence of a solution. This is the question that Muhammad Mahdi asked a few minutes ago, that if there is some limitations or some limits of the joint variables, how we can work on that. This comes into that picture. Basically, we can say that the solution exists. Let's think about it physically. A cup is here, put it that way, that you can see. A cup is here, and I would like to take this cup. If I can't take this cup, the solution exists. Maybe I can't find the solution, but the solution exists. But consider this cup is far, far away. It's very, very far. Put it here. And I am sitting in here. Let's put it here somewhere. Oh, sorry. It is here, and I am here. I just put it into the picture that the far, as I reach, I cannot get that. Yes? You see me? This means that there is no solution. We call it the robot workspace. Workspace is the space that a robot will work. Really sorry. Everything here, but we call that a workspace. Sorry. And it is interesting, the mathematical concept, after 20 years of thinking it is for me unbelievable. You have my voice, yes, you have, because workspace, a reachable workspace. It means that there is a solution, the inverse solution exists. If I can get that cup, if I can get to this point and this orientation. So, it is quite possible that there are some points in the space, not only the positions, maybe some orientations. If I put the cup this way, I cannot get it this way, you know? I can reach to this point, but I cannot get it the right way. The orientation and position is important. This way it is much easier, but this way, maybe I cannot get that because of my limitations in my arms. So the solution, if the solution exists, it means that this point is in the workspace of the robot. So we call it the solution exists. Look at here. If the end effector is within the reachable workspace of the robot, and consider that you could have two solutions as well. That's why we can have multiple solutions. It could be no solution when it is out of the space, out of the workspace. But when we are within a solution, I can get this, look at this again, this way or this way. Look at my point, this way or this way. I can reach to this point this way or this way. I have two solutions here. It could be two possible solutions, even more. We can have some robots with more than 64 solutions to reach to a particular point, at least mathematically. This will happen in parallel manipulator, not in even we have some robots which 1024 means 1024 solution to reach to a point. Unbelievable. So we call it a solution exists. Here I don't want to go to multiple solutions right now. In this I will give it to you next session. But here I will talk about reachable workspace. So this is another point. By inverse kinematic analysis, we can find the workspace of the robot. And it is very important to have the workspace. For example, you want to buy a robot that can paint. And you know that the car or the body that you want to paint is at least 2 meter by 2 meter large. So you need a robot that can move the 2 meter by 2 meter in a space. So you should pay for that. And the workspace of the robot is very important. Reachable workspace, the volume of space in 6 degrees of freedom, of course, in general, that the end effector of the robot can reach. And the volume in 6 degrees of freedom is somehow not imaginable. We have a volume in 3D space. We can have a position volume. It could be a square, it could be a whatever geometrical shape that we have when we have 3 degrees of freedom. But in robot, in a general robot, we don't have only 3 degrees of freedom. It was so simple if we have only position. We have 3 more other equations which relates to the orientation. You look, you will see that if this orientation is a bit hard, then the water will be, you know, it cannot be. The orientation is very important. I'm sorry, I just messed everything up, but I hope that my system is not very badly working. I'm sorry. But as you see, seems that my keyboard is full of water and our time is on. We call it, I'm sorry, we call it a workspace, a reachable workspace. You can understand the 3D position that we can get just by inverse kinematic. If our inverse kinematic solution exists, then we have this point in our reachable workspace. If it doesn't exist, if there is no solution, it means that this point that I'm reaching is out of reach. It is out of my workspace. Then we have another thing, and this is my final word, which is called the Dexterity space. Dexterity. Dexterity space. The volume of space that an end effector of the robot can reach with all configuration. It is very important that if I can get this point, I can get it in all direction, all orientation. Not only my hand can reach to this point, since this hand is designed by Almighty God, it can reach this point with all orientations. All orientations. Here, this way, all orientations. We call this Dexterity workspace. And dexterity is very important. And how we can measure the dexterity? Next chapter. We have a lot of things to work. Dexterity workspace, of course, is a subspace of the reachable workspace. And we have also a constant orientation workspace. And constant orientation workspace, when you want to visualize it, we call it kaw or gav in Farsi, but in English we call it kaw, constant orientation workspace. If you are looking for a gav in a robot, means that the volume of space that you can reach the end effector at that point, at least with the constant orientation. We want to have this perpendicular. You know, we don't want to have angular. If we have angular, this would be Dexterous workspace. But we need to be, you know, perpendicular, that this water doesn't, you know, give mess to all my stuff that I have done it just to remind you that this is the problem. Let me just drink a bit of what to make it a bit less messy here. A constant orientation that we can reach to this point, at least we call it the volume of space that the end effector of the robot can reach with constant configuration. At least with constant configuration. Theta is equal to 90 degrees, or theta is equal to 0 degree, or whatever we want. Maybe if we can have it with all degrees, then we call it this dexterous space. And why this is important, and it is very important that very hard to visualize a 6 degree of freedom space. We have only 3 dimensions to see that. But usually we have, for planar case, we can see that since we have only X and Y, 2 position and 1 orientation, we have only 3 degrees of freedom, we have only 3 frames, therefore we can visualize in the 3D space. But our physical space is not 3 space, it is 6 degree of freedom space, 3 degree of freedom for position and 3 of them for orientation. I will stop here before, you know, making everywhere wet here, but I remind you that there is a relation between mathematics and our physics, between the underlying mathematical concepts on kinematics and what we can really feel. And if I could possibly provide you the feeling of these issues, then you will enjoy, really enjoy solving that difficult mathematical equation. And I hope that we can continue on that, hopefully in the next session. Thank you very much for being with me and for giving very good thought and concept. And finally, please contribute in the course. I don't want just listeners. I want people who are playing with me with this game. They are painting with me this picture that we are hopefully painting until the end of this semester. If there is any question, I will be at your service, please. If there is no question, I wish you all health and prosperity and good day. Bye.